Okay, lesson 5, finding zeros of completing the square. Okay, we do have a live audience today, just as a reminder. So, you guys have done completing the square. Okay, we've done it. Now we're going to use it to solve. All right, we've done it in the past to go from standard form to vertex form. So now we're going to take and we're going to solve equations by completing the square. So you already know the process. Now we're going to take it just one more step to solve. So when we solve, we're finding zeros. Okay, we're finding where the quadratic crosses the x-axis. And last lesson, where we were taking the square root, our equation was always in vertex form. Think about that for a second. Your equation was always in vertex form if you were going to take the square root. If you were going to factor something, your equation is always in standard form. So we've got the quadratic equation, and this is clearly in vertex form. So now it says, find the zeros in simplest radical form. So if I'm going to find the zeros, I've got to set my equation equal to 0. And thinking about, because this is in vertex form, it lends itself very nicely to taking the square root. So you're going to start to find patterns that occur in the equations, in the original equations, to sort of tip you off as to what method is going to be best, or what method is going to be most efficient to get to your answer. Because after completing the square, we've got 2 more methods to learn to solve quadratics. So we're going to get very good at looking at the equation and saying, okay, yeah, this is in the best form to factor. This is in the best form to use the quadratic formula, which we'll get to later on, or complete the square or graph. So continuing here, we've got 18 equals x minus 2 squared. Take the square root. We have plus minus the square root of 18, but 18 needs to be simplified, and I think you guys are getting really good at simplifying. But to solve for x, to finish it up, I have to add 2 to both sides, and I end up with x is equal to 2 plus or minus 3 square roots of 2. I have a rational number, and then I have an irrational number. Okay, we're going to leave that just like that. Okay, that is your simplest radical form. It says, in part B, it says, find your answer to the nearest tenth. That is calculator work. I'm not going to waste our time with that. Just keep in mind you have 2 solutions here. You have the 2 plus 3 square roots of 2, and then you also have the 2 minus 3 square roots of 2. Because remember, it's a parabola. It's going to cross the x-axis, in this case, in 2 different locations. So it says, but of course, in order for us to find the zeros using the inverse operations, that means taking the square root, it has to be in this form. It has to be in vertex form. It says in order to do this, we need to complete the square, and you guys know that. You know to put something in vertex form, you have to complete the square. Why do you guys have case of the giggles? All right. Okay. So it says, consider the equation. We have standard form. Finding this, it says, find the zeros of the function first by factoring. So we know in order to factor, we have to set it equal to 0. We think sum and product. I'm moving through this rather quickly because by now we need to be very efficient in our factoring. Okay. So 0 product property, we set both our factors equal to 0, and we get solutions of 8 and negative 2. So my equation crosses the x-axis at 8 and negative 2. Now it says, find the zeros of this function by completing the square. Well, we know the answers ahead of time. We know we've got to get to those answers, but now let's complete the square. So when I think about x squared minus 6x minus 16, I still need to set it equal to 0. I'm still finding the zeros. Think about that process of completing the square. X squared minus 6x. Let's shove that constant over. And I need to make that perfect square trinomial. So I'm going to take half of that, right, and square it. So half of negative 6 is negative 3. But when I square it, anytime I square any number, I'm going to come out with positive. So what am I doing? I'm adding 9, but I can't just randomly add 9 to an equation. So I also have to offset it by subtracting 9. Now I have a perfect square trinomial. Perfect square just means a number times itself. We're sort of skipping ahead and saying, okay, it's x. What was this before we squared it? It was a negative 3. So minus 3 squared. That's just the shortcut way of writing x minus 3 times x minus 3. We skipped that intermediate step to save a little space and a little time. Combine like terms. Negative 25 equals 0. We have it in vertex form now. We've completed the square. Now we're set up to take the square root. What we learned last lesson. So how do I continue from here to get x all by itself? So I would have to add 25 to both sides. I'm running out of space here. X minus 3 squared equals 25. I take the square root. X minus 3 equals, when you take the square root, what do you need to remember? You can speak. Plus and minus 5. Michael's going to find his way out into the hallway in a minute. X minus 3 equals 5. And x minus 3 equals negative 5. So taking and solving, we end up with x equals 8 and x equals negative 2. Those two should be the same solutions that we got back by factoring. So right now, with this particular equation, look at the steps that it took us to factor. Now compare, look at the steps it took us to complete the square. With that equation, which one is the most efficient? Factor. So now it's going to lead into talking about the differences between factoring and completing the square. When's it going to be best? It would probably seem to many students a bit redundant to have two methods for finding. But it says, let's illustrate why completing the square is important in its own right. Meaning, when is it best to complete the square? Because clearly in that one it's not. So let's look at this equation that they gave us. And instead of doing A first, let's do B first. It says try to factor this. X squared plus 6x plus 2 equals 0. Think sum and product. Can I come up with two numbers that multiply to 2 but add to 6? What are the only factors of 2 there are? 2 and 1. Can that ever add up to 6? No. So we can't factor. It's not possible to factor. So when it's not possible to factor, that's when you think about completing the square. So I'm going to write that equation down. Set it equal to 0. And I'm going to start to complete the square. X squared plus 6x. Shove the constant over. And now take half and square. So half is 6 is 3. 3 squared is 9. So add 9. But also subtract 9. Now we have our perfect square. x plus 3 squared, combined like terms, negative 7 equals 0. We add 7 to both sides. So x plus 3 squared equals 7. Take the square root. X plus 3 equals plus and minus the square root of 7. Now, the square root of 7 can't be simplified, so at least we have one less step to do there. Get x by itself, so we'd subtract 3 and we end up with negative 3 plus or minus the square root of 7. I have a rational number plus and minus an irrational number. A rational plus an irrational, or a rational minus an irrational, always is going to produce a what? An irrational number. Do we know factors of irrational numbers? We don't. Okay? That's another reason why this one was not factorable. You can't do it. Okay, it says, what can you conclude about zeros that are found by the zero product law? Factoring. We just said it. Okay? Those that can be factored produce rational roots. Or rational zeros. Okay. All right, go ahead and flip the page. So it says, we now have a variety of tools at our disposal to find zeros and the turning point. Some cases we can factor. In other cases, we need to put it in vertex form to be able to take the square root. So it says, let's analyze this quadratic. And it's written in standard form. It says, write this in vertex form and state the coordinates of the turning point. So if I'm going to put this into vertex form, I've got to complete the square. But, we should take this out. Remember, when we complete the square, our A has to be equal to 1. A has to be equal to 1 in order to complete the square. I'm still going to shove that constant over. So if I factor out the 2, I'm going to get x squared minus 2x. Now start the completing the square. Take half and square. So if I take half of negative 2 is negative 1 squared is 1 plus 1. But really, I didn't just add 1. I added 2 times 1, which is 2. So to offset adding 2, I have to subtract 2. So I got f of x is equal to 2. Let's factor it. It's x minus 1, the quantity squared. Combine like terms, negative 18. So it says, what is the vertex? And state, put it in vertex form and state the turning point. So what is the vertex here?
1 negative.
You got it. 1 negative 18 is the vertex. It says, use your answer from A, find the zeros of the function. Okay, so if my vertex is 1, excuse me, 1 negative 18, let's take this and find the zeros. So 0 equals 2 times x minus 1 squared minus 18. I would add 18 to both sides. So 18 equals 2 times x minus 1 squared. Divide by 2. I'm not going to show that just for lack of space here. Take the square root. Ooh, this one's going to be kind of nice because we've got the square root of 9, okay, which is perfect. So we have plus and minus 3 equals x minus 1. So I'm going to come out with 2 rational roots here, okay, 2 nice, neat numbers. So if I add 1 to both sides, I can take this and say, what is 1 plus 3? That's one of my roots, which is 4. And then the other one is 1 minus 3, which is negative 2. So my zeros are 4 and negative 2. So by looking at those roots right now, even though we completed the square, if those roots are rational, was that function that we initially started with, could we have factored it? If we produced rational roots, could it be factored? Yes, absolutely. The only time it can't be factored is if we produce irrational roots. Okay? So now it says, determine the function's y-intercept. Guys, I would take right now, because we're given it in standard form, look at the standard form. In standard form, where is the y-intercept standing right out? The c, the constant, yes. That right there, there's my y-intercept. So if I'm going to write it as a point, my y-intercept is 0, negative 16. Okay? Now, in part D, it says they're asking you to draw a rough sketch of this because I kind of wrote over a lot of this. What's the important information that we just got out of this problem that you could put on your sketch? We could put the vertex on there. How does this open? Does it open up or open down? It opens up because we know that that's positive. We also know the y-intercept. That's another key piece of information you could put on your sketch. And we know the roots. So 4 pretty key pieces of information, well 5, knowing that it opens up to come up with a sketch. Okay? Now it says, let's see if we can go in the opposite direction. So it says a quadratic function pictured has a leading coefficient equal to 1. So the a is 1. Positive. Write an equation of this quadratic in vertex form. Then it says write it in factored form. And then it says how could you establish that these functions are equivalent? From this graph that's given to us, I go right to that. I go right to the roots. And I don't think, oh no, we could do either. Okay, I'm going to do the vertex too. So the vertex is negative 1, negative 4. So if we know the vertex, negative 1, negative 4, we can write it in vertex form. Because what's our standard or our general equation? A times x minus h quantity squared plus k, where h and k are the turning point. So we can say, and we know what a is because they told us it in the problem. So it's 1, I'm going to leave that 1 out, x plus 1 squared minus 4. I've got it in vertex form. Now I want to write it in factored form. Now I could go about it a couple ways. I could take this vertex form, do a little algebra to it, get a trinomial in standard form, and then factor it, but that's going to take a little bit of time. What did the problem already give us? It gave us the roots, or the solutions. So my roots are x equals 1, and what's my other one? X equals negative 3. So work backwards from there. So we have the solutions. Now I want the factors. Where did they come from? So they came from x minus 1, and the other one came from x plus 3 equals y. That's the equation in factored form. And it says, how could you establish that these are equivalent functions? What could you do? Okay. Do a little algebra to that. Do a little algebra to that. Get them both in standard form. and you'll see that they're exactly alike.